Video recording started, so thank you once again. I apologize once again for being a bit late for some hiccups during traveling. So your question is related to where to find the recordings. So if you go on my website, there is the YouTube channel, and there are two ways. So the first one is to follow the link of my YouTube channel, and in the YouTube channel you see there are the playlists. So in the playlists you find Harbour Engineering here, and Harbour Engineering, I think everything should be there. 21 February, 28, 6, and 13 of March. So everything is there, and in the YouTube channel. Okay, and another way is through Virtuale. If you go into Virtuale, and then of course you log in, you find something a little bit different with respect to my main screen, but in any case you should find the link to your, one second, otherwise I make mistake. Okay, you should find the link to the course, and the list of the courses is different for you. If you click on Harbour Engineering, you go to Panopto, and here you see that there is a list of the registration. It's in Italian, because if you want to win English, you have to switch to the language. And there is the recording, so March 13, February 28, and then this is March 6. I think it looks like, and then there should be also, yes, February 21st. So everything is also in Virtuale. The only difference is the same video. The only difference is that in YouTube, sometimes you get advertisements. In Virtuale, you don't get them, but it is the same video, okay? And also you should be able to find the link to the recordings, at least the most recent ones, under the chat of Teams. But I'm not sure of this last information. But for YouTube and Virtuale, it's there. Is it clear? Okay. And if you miss something, just let me know. Just keep in mind that in some of the cases, I think there was a break in the recording for technical reasons. So I don't remember if it was the first lecture rather than the second one. There was a break. And finally, just keep in mind that there is also the break recorded with audio off and video off, because I prefer not to split in two videos. Okay, now let me then go to forcing estimation for Harbour design. So last time we got more or less here. We discussed already wind forcing, and you know how to compute it. And remember, please, that I mentioned to you, if you can memorize the relationship here for wind forcing, it's one of the few that I ask you to kindly make an effort to memorize, because it provides an example. And then the other forcings are determined with similar relationships. And I don't think we need to remember each one of them. If you remember this one, equation 1, then the concept is the same. It's unchanged for, as you will see, for wave forcing and current forcing. I just want to remind you that we are discussing in terms of forcings, wind forcing, which is the most important, wave forcing, which we will discuss today. We already started, we will finish discussing it today, and forcing originated by currents. This is what we discuss, okay? So we already introduced the wave forces, and I think we finished the last lecture by discussing the rogue wave or monster wave. And then we discussed previously how to estimate a design wave, or a wave to be used for the project, okay? Design wave is a terminology that is used by some textbooks and not by others. But for design wave, I mean the wave that we use in order to size with the project the infrastructures and structures, okay? And of course, the design wave is a kind of extreme wave. I think that Professor Archetti probably in some of the courses already mentioned to you that we can estimate extreme waves by using wave data that derive from wave monitoring, meaning that we have observations taken at different time scale of wave height. Usually what we are given is the wave height, which is the elevation difference between the crest and the through. So if this is your wave, okay, and this is the mean sea level, okay, this is the through. Let me just remove this line. This is the through. And this is the crest. Okay? And the wave height is this difference here. It's the distance between the crest and the through. Okay? It is this one. This is wave height. Okay? So what we have is observations taken at different time steps. Sometimes you are given the monthly maximum. Sometimes you are given the weekly maximum. Sometimes you are given the annual maximum. It's important that you are aware of the time step. Usually it's not a continuous measurement. So you are not given a continuous recording, meaning every 1 minute, every 30 seconds. Usually you are given what is called a block maxima, where block is intended as a time span. So when I say weekly maxima, it's a type of block maxima, where the block is the week. Usually we refer to monthly block maxima, which give you the wave height in each month. Okay, so basically you are given observations, and on the basis of these observations, you have to estimate your design wave. Okay, design wave, and we already said that the design wave is usually a function of the return period. Usually guidelines, rules give us the return period, and we discussed already the typical return period for structures, for berths, and for mooring lines, fenders, etc. We said that based on the life expectation of what we are designing, then we are given, depending on the life expectation, we are given the return period of the design. Okay. And of course, why sometimes we are given monthly data? Because sometimes you specifically need to estimate a design wave that refers to a specific month. For instance, you may be involved in the design of an harbor that doesn't work during the winter, because maybe it's a touristic harbor. So during the winter, you don't have any boat, any ship berthed there. So if during the winter you don't have any use of the harbor, it's not required that you make your design basing on the winter design wave. You refer to the months where you are using the harbor, like from April to September. And then if you have monthly data, you can, for each month, estimate your design wave. So you know that in April, with a return period of 10 years or 30 years, you may expect a wave height of 3 meters. In May, with a return period of 30 years, you may expect a wave height of 1.5 meters. During summer, probably lower in our continental climate. During summer, probably you have a lower extreme wave. So for each month, you can estimate your design wave. Or if you are interested in only the max value of wave height between April and September, you can pick up from your data the max in the block April-September for each year. Okay, so if you have like 30 years of observations, you get the max from April to September in the first year, and so on. And then you get 30 values. And then on these 30 values, you estimate a probability distribution, which, depending on the reference period, T gives you the design wave. Okay. Of course, you need specify the minimum length of the observation period. Because it's clear, if you have an observation period of only 1 year, you cannot estimate the design wave with a return period of 30 years. You understand that? It's quite obvious. I mean, if I want to get an idea of the wave that may occur once every 30 years, I cannot get this idea from only 1 year of observations. It's quite obvious. You can understand that if the return period is 30 years, at least we would like to get 30 years of observations in order to get an understanding of the wave height that may occur once in 30 years. Okay. Actually, if we want to be reliable, we need a longer period, a longer observation period, longer than the return period. So if you have 100 years of observations, then you can estimate the design wave with a return period of 20 years in a very reliable way. Okay, because you have observations covering a time span that is 5 times longer than the return period. As a rule of thumb, we say at least you need a length of the observations that is at least as long as the return period. At least. If it is longer, much better. And then you may ask the question, and what if I don't have any observations? Because this is actually quite common. If you look at the database of wave data, you will see that it's unlikely that you get data for more than 50 years, because actually ocean engineering is, and harbor engineering, but in general, marine engineering is a young discipline. Basically, we started to study the dynamics and the weather of oceans before the Second World War, because during the Second World War, they had the need of understanding the dynamics of oceans because they had to fight over the oceans. They had to plan attacks at the lands by releasing people from the ships. And therefore, they had to know how to predict the dynamics of the ocean. This stimulated the onset of ocean engineering, oceanography. And then they started observing, because of course you need observations. They started observing. So you will find data that in some cases go back to 1950, but it is unlikely that you find wave data earlier than that. And therefore, if you are very lucky, you may rely on observations for an observation period of 70 years. But very often you may find no observations, or you may find a limited length of the observation period. So you may ask, okay, how should I deal with this situation? Of course, you can estimate a probability distribution even on the basis of a very reduced observation period. You can do that anyway. Okay, so if I need to estimate the design wave with a return period of 20 years, and I only have 5 years of observations, I can estimate my probability distribution. I can fit a probability distribution anyway. Also, there are techniques that aim to extract the max of information from the available data, which we are not discussing. So what I want to say, and what I wish you to remember, is that you have indeed techniques for for estimating. You have the possibility, you have methods for estimating the design wave with whatever return period, even on the basis of a very reduced data sample. But you have to be aware of uncertainty. So you have to know that if your observation period is shorter than the return period, you are very likely to get a lot of uncertainty, and therefore you have to introduce a proper safety factor. If the guidelines tells you to adopt a safety factor, for instance, we discussed the GAST factor, which is something that can be intended also as a safety factor, correction for uncertainty. If you are suggested to use a safety factor of 1.5, maybe that you can increase it to 1.8 or 2. Of course, you have to check what is the impact of this. I mean, you have to check what is the cost, the additional cost of the infrastructure. You have to check what is the additional environmental impact if you size a structure or infrastructure for greater safety factor. But this is a possible way. You may have another question like, and if I don't have any data at all, what should I do? Okay, I just would like to mention, and that's it, that there are techniques. There are techniques that we don't discuss, which may allow you, with an even greater uncertainty, to estimate design waves for ungauged, we say, ungauged meaning unmonitored sites. So what we said is, okay, once the return period is assigned by guidelines or by my own determination, we can fit a probability distribution. I think Professor Archetti will mention or already mentioned to you the Gamble distribution. Typically, we use the Gamble distribution. And then we get an estimate of the design wave, what we call the design wave. Okay. Why do we need this estimate? I just want to remind you, because the design wave is pushing the ship, is crashing against the ship, and it originates a forcing on the mooring points, a forcing on the mooring lines and mooring points. And this forcing should be added to the wind forcing. Okay. Is it clear, the summary that I made? Okay. Let me just mention one thing that it is not very clear in the literature. This design wave, it is sometimes called significant wave height. So you will find some web pages or textbooks that use this terminology, significant wave height. Thank you very much. This is a good idea. Thanks. Thanks a lot. Significant wave height. So don't be concerned. If you see somewhere mentioned estimation of the significant wave height, it is what we may call design wave. Okay? But actually, there is something more that I should say, because in the terminology of ocean engineering, significant wave height has a precise meaning according to some textbooks. So I think I should also give to you this precise meaning, because I think you need to know it. Because the term is used in an ambiguous way. So sometimes it is used to mean the design wave for a given return period. So you may find some references saying estimate the significant wave height for a given return period. Okay, but you may find other references providing a more rigorous definition of the significant wave height. And what is this more rigorous definition? Let me just show you. First of all, there is a Wikipedia page that is very clear, from which I copied something, okay? And let's read it. In physical oceanography, the significant wave height is defined traditionally as the mean wave height through to crest. Oh, sorry, through, I made a mistake. It's without the H. I'm sorry for that, okay? Through to crest of the highest third of the waves. So, again, the mean wave height through to crest, to crest of the highest third. What does this mean? It means very simply, let me open a R console to explain to you what is the meaning of this, okay? And let me just open R. But before working on R, I think it's better if I make a sketch. So let's suppose that you have wave data, okay? Data of wave height. Okay, so these are my wave data. You could put them in Excel or into R, and then I will put some wave data into R to show you. And then you get this data, which may be collected maybe maximum in a year, in a given year, or monthly maximum. Okay, you have data. Okay. Now, this data, you can order them in increasing order. Okay, increasing. This is very easy in Excel and R. Okay, so this is the mean, and this is the max. Okay, and then you get the lowest, the highest, 1/3, highest, 1/3, 1/3 in terms of number of data. Okay, so if you have 10, you get the last three and a half. Okay, and then you compute the mean. Okay, and then on this mean value. This is the way some textbooks define the significant wave height. So let me just now on R make this computation. Okay, let me just modify the font here, sorry. The font, let's use 20. Okay, I clear the screen. Let me generate random numbers, which I may adopt as wave height, okay, like annual maxima, to generate these random numbers, because I don't have a vector of wave data to download, ready to be downloaded. So let me just generate an artificial series, and we can generate with the function from the log normal distribution with this function, which means random generation from the log normal distribution, RL norm. And let's take like 100 data. I'm not specifying any parameter for the log normal distribution. It's okay. If you want to see a plot wave data, sorry. Okay, this is the plot. Let me just show it with lines. Okay, this is the plot, and this could be wave data. Okay, you don't see the sinusoidal shape because these are, as I said, block data. So maybe yearly maxima, monthly maxima. Okay. Now what we have to do is to order the data in increasing order. This is very easy. I can make wave data 1 is equal to sort into R is very easy, sort wave data. If you just put sort, it's ordered in ascending order. If I make a plot, you will see plot of wave data 1. This is the plot. It's in ascending order, okay? Now, these are 1,000 numbers. The highest third is from, in the order data, is from the data number 667 to 1,000. So if I compute the mean of wave data 1 from 668 to 1,000, okay, this is 3.58. This is, according to this definition, the significant wave height. Okay, so I order the data in ascending order, and then I am taking the highest 1/3, and then I compute the average, the mean. Okay. Now, what I did, it's like a frequency analysis, because what I did is to refer to a class of less frequent data. The highest 1/3 is less frequent data. So I made a selection based on the frequency, and then I computed the average, which is another frequency analysis, because the average is a kind, in terms of frequency, midway in this highest third. So you understand that in doing that, implicitly, I am associating to this number mean of the highest third a frequency. So this mean of the highest third, what frequency does it have? Does it have? Clearly, it has an assigned frequency, and then an assigned probability, and then an assigned natural period. So an interesting question is, according to this definition, what is the natural period of this number? Okay, this is a nice question. So let's suppose that these are annual maximum. So my plot that was on the screen here. Let's suppose that these are annual maxima order, okay? So what is the frequency? What is the natural period of this mean? First, let me recall one relationship which is in the web page that is not on the screen now, but it's there. Let me just share the screen because I forgot in here. Okay, and let me put, here it is, perfect. 1 second. I wanna link this. Okay, I wanna put also on the screen the blackboard. So let me recall this relationship here, which is in the web page, as I said. Second, it's here. It's the relationship between probability and retro period, or let's say we can write that probability is equal to retro period minus 1 divided by retro period. Or alternatively, we can derive the retro period here. So this relationship can be written in this way: Tp equal T minus 1, and then basically you can write T, which multiplies probability minus 1 is equal to 1. And therefore, we can derive the return period. Sorry, there is something that is wrong here. So, yeah, yeah, okay, this is minus 1, okay. And then the return period is equal to 1 divided by 1 minus p. What is p? P is probability of not exceedance, okay. P is probability of not exceedance. Okay, so my question was, what is the return period according to this formula of this number here? Average of the highest 1/3. Good. Let's go to R again. The number is 3 point, it is this one, okay? The number is this one. Now, in order to apply this relationship, I need to know the probability of not exceedance, probability of not exceedance of this number. R can help me because I can compute it as PL norm of the number. It's 0.89. Okay, so return period is 1 divided by 1 minus 0.8990896. It's 10 years. If the data are recorded once every year, if the data are annual maxima, the return period of the significant wave height defined in this way is 10 years. So this is what I wanted to discuss with you, because actually in some textbooks, as I said, they define the significant wave height in this way, which means that they are suggesting to size structures with a return period of 10 years, which is a little bit low for, as we discussed. We discussed that for birth structures, usually we take a return period between 30 and 50 years. Okay. This is for the sake of clarity. And if we go to the web page, what you see here is a description of this discussion. I'm sorry, here I made a mistake, and there is, I see it now, there is a formatting problem, so don't be, I call significant wave height HS, and S is a subscript, and I forgot, I wrote this yesterday night, and I forgot to put the subscript in the correct form, okay? Let me correct it, okay, not right now. Okay, so, quoting from Wikipedia, first of all, here you have a figure where you have depicted from Wikipedia is taken the probability distribution of a given probability distribution of wave height. I use the log normal distribution. Actually, they are using here the Rayleigh distribution, which is widely used for modeling wave data. And so if you look at the distribution, this is a probability density. Okay, remember what is probability density, and remember that the probability of not exceedance is the integral of the probability density. So if you look at the probability density here, you see that there is the 1/3 of waves that is depicted here, and then the average of this 1/3 is the significant wave height HS. If you look at all the data, you can see depicted here the mean value, the mode, which is the value with the highest probability density, and the median, which is the value that splits the sample into part of the same size. If you want to understand more on these terminologies, probability, you have links here to better understand. It's not necessary for our specific purpose. For our specific purpose, for your exam and your education, if you learn what is the significant wave height, if you learn what I discussed here, that's fine. And here, there is a mention that you see that if the significant wave height, they make an example. No? Let's suppose that is 10 meters, okay? Then they say, okay, 1 in 10 will be larger, which is precisely meeting the definition of retro period. So if you have a significant wave height of 10 meters, they say 10 meters plus something, because they refer specifically to this distribution, means, so the significant wave height means 1 in 10, which is what I told you, 10 years, for retro period of 10 years for yearly data, which means 1 in 10. One interesting indication here is that if you want to get 1 in 100, you should get about 1.5 the significant wave height. So if you want a retro period of 100 years, you should get 1.5 the significant wave height. And this is an empirical rule. Don't take it rigorously. It's a rule of thumb, but it is quite precise for wave data. And if you get twice, more or less twice, the wave height, you get 1 in 1,000. It is interesting if you remember this. So, because sometimes you may need to give a magnitude, an order of magnitude, like I have an estimate of the wave height for a 10 years retro period, and I need to quickly provide an estimate for 100 years retro period. What should I do? 1.5, more or less. I mean, it's an empirical rule, okay? But it is interesting. And keep in mind that the concept is, if you have a variable, an extreme variable to describe, a small increase in the variable implies a larger, much larger increase in the retro period. You see here, from 1 in 10 to 1 in 100, I could say from 10 years retro period to 100 years, there is a factor of 10. I am increasing 10 times, but the corresponding wave height is increasing 1.5. So keep it in mind. When you describe extremes, in general, environmental extremes, rainfall, river flow, wave height, and you get an estimate for a given retro period, I said 10 years, and you are required to make a guess of the corresponding extreme for 100 years retro period, keep in mind the factor 1.5, okay? It is something that it is basically correct. Here, of course, you see that the rule is rigorous, but it is rigorous because they refer to a very specific probability distribution, which is the Rayleigh distribution. Okay, some additional considerations, which are written here. So I'm talking, but everything is written there. When you design an Harbour, you should consider any evidence that may allow you to design for a lower size, to save money. So to design with respect to a lower wave height. What could be this these evidences. First, seasonality. As I said, if you have an harbor that is not working during the winter, you are not required to size the harbor for the max wave height during the winter. Refer to the operational period. And it makes a big difference. It makes a huge difference, whatever is the sea where you're working on. I mean, the biggest storms occur during the winter season, which in this region is from November to March. Okay, in other regions, of course, different. So refer to the season. You are allowed to do that. If you don't use the harbor, no ship is there during the winter. You don't need to size it for the extreme wave during the winter. Second consideration, second evidence. Are you allowed to unberth the ships in case a storm occurs? Because what is the problem? The problem is the mooring points. The problem is the bollard. The problem is the berth that is subjected to extreme conditions when you get extreme wind, when you get extreme waves, and these extreme conditions are transmitted by the mooring lines. Are you allowed to release the mooring lines, to unberth the ship in critical conditions? In some cases, you are. And you can predict these critical conditions. Remember that a storm in the sea is not something, okay, windstorm may be quite sudden, but usually we can predict it. And wave storms are not sudden, we can predict them. We have efficient forecasting methods. So on the basis of our forecast, we could unberth the ship. And this is possible, and it's not dangerous because, I mean, what is dangerous is if you break the mooring lines, if you break the structure of the berth, then it becomes dangerous. But the ship is equipped for navigating into the open sea in extreme conditions. It's designed for that. So in an harbor, you have a sheltered area. You don't have such extreme conditions. The ship can go into the harbor and stay there and take the waves, and it's not a problem. The problem is if the forcing is given, transmitted to the mooring points, so you can unberth. So if you can unberth, you may be allowed to design for a return period of 10 years. Because if once every 30 years you get a very extreme storm, you unberth the ships. Okay, this is written here. Okay, permanence in any condition or permanence only in quiet conditions. Keep in mind that the design wave height is to be computed for any possible wave direction. And this is a complication of waves. When you talk about other variables like rainfall, rainfall doesn't have a direction, it's only the vertical direction. Okay, wind and waves, of course you have to compute for any direction. So when you collect wave data, you get the wave height as an information and the wave direction. So you have to compute the extreme wave for any direction because you have to check the berthing conditions for any direction. Okay, finally, these are, I think probably I already discussed them with you. These are indications of orders of magnitude of significant wave height, so design wave height for some specific vessels, like for a displacement up to 3,000 tons, you see here the significant wave height. This is interesting for getting an order of magnitude. And you see that even for large ships, the significant, the design wave that is suggested is a couple of meters. So we don't have to design with respect to waves that are, I mean, 10 meters, okay? Like the waves that they can find in the open sea. And these are, as I said, the orders of magnitude. Okay, good. Questions? Now we need to compute the formula. We have to look at the formula for compute wave forcing, because up to now we discussed only the height of the wave. And we will see that the height of the wave gets into the formula. Okay. Questions? Before we move forward, let's remember the terminology of the movements. And I tell you because I need to remember myself. Sometimes I make some confusion. So we have 6 degrees of freedom. So we call yaw the rotation around the vertical axis of the ship. We call pitch the rotation around the transversal axis. And we call roll the rotation around the longitudinal axis. Okay. And then in terms of translations, sway along the transversal axis, surge along the longitudinal axis, and heave along the vertical axis. Okay. We will see that you may remember that I think we mentioned it when we talk about wind forces. We assume that wind forces don't cause a movement along the vertical axis. They don't cause heave. And the rotation is only induced in terms of yaw. When we have wind forcing, we assume that. For the wave forcing, of course, we have to consider heave. Potentially, the wave forcing can originate heave, can originate pitching, can originate yaw, can originate surge and also sway. Okay, so wave forcing may generate more movements with respect to wind forcing. Of course, in some cases, the wind forcing generates a wave forcing, but we are treating them separately. So wind doesn't provoke an up and down usually. Okay, the up and down is provoked by the waves. Now, of course, you understand that a forcing that possibly originates movements along the 6 degrees of freedom is a complex forcing to describe and to estimate, because it depends on the interaction between the waves and the body of the ship. And this interaction really depends on the direction of waves with respect to the longitudinal axis of the ship, and depends also on the geometry of the ship. So it's extremely complicated. And there are extremely complex numerical models to analyze this possible interaction. Actually, in naval engineering, ships are designed on the basis of very complicated numerical models. I think you may have had some information on that. Here, we need to simplify things because, the purpose here is to estimate the forcing along the mooring lines, the bollard points, and let's try to simplify things, but be careful. I am simplifying according to the indication given by the Spanish rules, the rules that I made available for you to download here, which are a good reference. On the other hand, in specific situations, you have to check what the guidelines suggest, because the formulas that I am now mentioning to you, they are very simplified. They may be acceptable in some countries, may be acceptable for small harbors, may be not acceptable in other situations. So you have to be careful about that, okay? Okay, now, first, before a final consideration, before introducing the relationships. The final consideration is related to the wave period, because the wave forcing, in principle, depends on the wave period, not only on the wave height. And the relationship that I will show you don't consider the wave period, they only consider the wave height as an independent variable, which is fine, but you understand that the same wave height with different periods can cause different forcings. And in particular, let's see these indications, okay? Mooring line forces are almost entirely induced by waves of period longer than 20 seconds. with major contributions occurring in the period range 40 to 100 seconds. So up to 3 minutes of period. 3 minutes is quite a long period, okay? Rolling, rolling, it's here, okay? Rotation along the longitudinal axis. Rolling is triggered primarily by swirls in the 13, 19 second range. This is quite understandable if you think about rolling. I mean, it's a movement that is typically occurs with high frequency. High frequency means a short period, okay? You wouldn't imagine rolling like a very small one, okay? A very long movement with a very long period. This may be the case of surge. Surge means, sorry, not surge, pitching and also surge in terms of translational movement. These movements along the longitudinal axis, rotation around the transversal axis, are slower with respect to roll that is expected to be a bit more frequent, okay? Now, pitching is small and insensitive to wave period, actually, whereas heave motion tend to be more sensitive to wave at long periods. Heave, remember, it's this one. And now, why? Why these differences in period? Okay, because there is one phenomena that you should take care of, and you should be concerned of. It's a phenomena that we will discuss later. It's called resonance, and you understand what is resonance, okay? So it means that if you have a wave that is fluctuating at the same period of some characteristic period of the ship, then it's a problem because it may self-reinforce the movement, okay? So if you look at these movements, roll, it's clear it's what is a characteristic period of rolling of the ship. It's short because it's a movement that doesn't involve a large displacement of the ship. I mean, it's movement around the longitudinal axis. So it's quite frequent. While a movement like pitch is moving, I mean, a larger part of the ship. It's something that is slower. So you have to think at what could be the characteristic period of an oscillation of the ship. And I give an oscillation, okay? And you have to be careful that you have to be concerned if the period of the wave is matching, is getting closer to the characteristic period of the ship. In fact, the flutter effect, flutter, is precisely given by resonance. Flutter means, you know, like when you get a glass of wine and you move it a little bit in order to get the wine moving. You have to be careful because if you move it at the same frequency of the oscillation of the mass of wine inside the glass, you get the wine pouring outside. And it is called flutter effect for ships because even a stable ship, if they get into wave regime that has a period that is close to the characteristic period, one of the characteristic period of the ships, they can start moving with larger and larger oscillations until they may collapse. Okay, and this is something that you have to be aware of. So this is why here they put these indications. Okay, in technical terms, just be aware of mooring lines. Okay, and so the period I am concerned of is between 40 and 200 seconds, and rolling and pitching, rolling is a shorter period, and pitching is in general it's insensitive to the wave period, but it's more it becomes more delicate for longer periods. Okay, now let's look at the relationship. The relationship, let me see if I can magnify it a little bit. I'm not sure it becomes larger. Yes, it is large. So let's, first of all, we have two of them, lateral or transverse wave force, longitudinal wave force. And the formula is more or less the same. It's, and you can recognize here more or less the same concept that we used for wind forcing, because the forcing is assumed to be proportional to the energy of the wave. Like for wind, the forcing was proportional to the energy of wind, and the energy of wind was estimated through the square of the wind velocity. Here, we are estimating the energy of waves through the square of the wave height. Okay, now, let's look at the formula. We have two coefficients, first of all, two coefficients that are called CFW, CDW. They are called CFW, the water plane coefficient, and the CDW is called the depth coefficient. We will see how to estimate them. There are abacuses for, we can estimate them through an abacus, okay? And so let's forget about them. They are dimensionless. Now, gamma W, density of seawater, we had for wind forcing density of air. Here, the forcing is through water. So we estimate, we plug in the density of seawater there. Remember that the density of seawater is larger than the density of fresh water. The density of fresh water is 1,000 kilograms per cubic meter, as you remember. The density of seawater is depending on salinity, but usually we take a value of 1024 kilograms per cubic meter. There is quite a significant difference, as you see. Okay, not that much, but I mean, it's 2.4%. It's not so negligible. Yeah. No, here we don't make a difference between pressure and which I think is what you are calling inertia, and drag. Here this representation just makes a decomposition along the longitudinal axis and the transversal axis. And each of these two components is assumed to encompass everything, because with waves, actually, you don't have drag. With waves, there is no movement of mass unless they break. So within an harbor, we suppose that the waves don't break, it would be a problem. So the waves are not associated to a movement of mass. It's just a movement of energy. But this movement of energy brings the ship up and down. No, it's dependent on the depth of the water through the depth coefficient. And this is...
forming close to the coast line.
Yes. Why?
We have the transition of the mass, but in deep water, we have just moving.
Yeah. Yeah, this is a statement, what you're saying. Yeah, I agree. I fully agree. So where you have sediment transport close to the shoreline because it's after breaking. When the waves break, the movement of energy is transformed in a movement of mass. And therefore you have drag. And sediment transport is originated by drag because it's mass movement. But in open ocean, as you said, it's just up and down, and there is no movement along. Because they don't break. Actually, there is a movement along the vertical direction, but in the horizontal directions, you know that there is a very small, very limited movement, in an orbital movement of the fluid particles, but it's negligible. So in an harbor, we don't want waves breaking, and therefore we adopt a depth of the harbor so that the waves don't break. And therefore, it's basically an up and down. So there is no drag. And or drag is very negligible, you know, because it actually there is no movement of the water with respect to the surface of the ship. We will see that in currents, when we will deal with currents, indeed there is a drag force because currents it's a movement of mass. But with waves, you don't have movement of mass. These are just two components, and you see that they are identical. The only difference here is the angle, sin square phi cos square phi, because it's a decomposition of the forcing that is acting along the wave direction, and a decomposition along the longitudinal axis and the transversal axis. I'm not sure if I was clear. Yeah, let me make a sketch. I think I can delete everything here. Well, let's suppose that you have see, you have a berth here and a ship. Let me just draw it as a rectangle in order to simplify things. And let's suppose that you have waves coming along this direction. So let's put it here. Okay. And this direction is forming an angle with the longitudinal axis, which is P. So what you can see in these two formulas is a decomposition of this forcing, this one, along two directions, one here and one here. This is transversal. This is longitudinal. So what the forcing, this one, is given by CFW, CDW, and then, sorry, CDW, and then there is gamma W, and then there is HS squared. And then there is, I think, D1. Let me see what is D1, sorry, D prime. Projection in the direction of the incident wave, okay? So, which is, okay, it's D1, D prime. And then the decomposition along the two axes is obtained by multiplying for sin squared and cos squared. And just in order to complete the description of the variable, specific weight of water, okay, here they say 134 tons per cubic meter, and it's one. I mean, if you say tons, this is 1.034. So it's 1 ton plus 34 kilograms. Okay. Earlier I said 1024 kilograms per cubic meters, and of course 1 ton is 1,000 kilograms. Okay, and then HS is our significant wave height, and this is phi, the angle of the wave direction to the ship center line. It's this one, and here you have d prime, projection of the ship length in the direction of the incident waves. So it can be expressed depending on the beam B and length between perpendiculars. And then multiplied by sin phi cos phi. Okay. And here you get the sin squared and the cos squared because is the result of the decomposition. I mentioned the abacus for the estimation of CFW and CDW. CFW depends on the wavelength and the draught of the ship. CDW depends on water depth and wavelength. Once again, just 1 second, I go back to see if I forgot something. Okay. That's it. Okay, these forcings, it's not written here. We can assume for simplicity that they are applied to the center of gravity of the ship. Okay, for simplicity, because actually the things are more complicated, but for simplicity, we can apply them to the center of gravity of the ship, the overall center of gravity, okay? Okay. So, as I said, resonance, okay? We already discussed it. And here I put online today a table which gives, taken from the Spanish standard at these pages. And which gives, let me make a correction, period in seconds. It's not written seconds here. I want to correct it soon because otherwise I forget. So let me make the correction. Give me 1 second. Okay, good. And then I will refresh the page, but I prefer to make the correction from my PC because it's faster. Okay. Because when I get too many things to change, it becomes a problem to remember everything. So it's table 1. Okay. So it's table 1, it's table 1. Okay, it's characteristic periods in seconds for given ships. Okay, and then another correction here. And then there was the sub. So 1 second. This is a bit more complicated to find. Let's see. Significant wave height. Okay. Okay, here it is. Significant wave height. Okay, let's see. HS. But I think I can keep HS in this way. Okay, I will save it now. Okay, now let me refresh the page as soon as it is saved. Okay, let's refresh it. Okay, so these are characteristic, as I said, periods for given ships. And you see that for the different movements, you have different characteristic periods. This to give you an idea of what are the characteristic periods of given vessels and therefore what are the wave periods you should be concerned of, depending on the ships that you are planning to host. Okay, here there is a small section just for your information, wave loads by breaking waves against vertical walls, and this is the order of magnitude of the pressure, and it's about from 150 600 kilonewton per square meters. And then currents. Okay, do you have any additional questions related to wave forcing? As I said, you don't need to remember these, okay? No need to memorize these two relationships. If you want to be very prepared, it's just enough that you remember the concept, which is wind forcing is estimated depending on the energy of the wave, which in turn is estimated depending on the significant wave height, and dimensionless coefficients are added in order to take into account the local characteristics of the harbor, and in particular wavelength, expected wavelength, and expected depth. And depending, of course, there are two components which are estimated by depending on the angle phi between the wave direction and the ship center line. That's it. Okay, I think we can start discussing currents. And currents are a movement of mass, so they are different from wave forcing, of course. They originate a pressure against the body of the ship, and they also originate a drag. It is, again, a complicated phenomenon phenomenon, which we assess. We assess the forcing by taking a simplified approach. Now, what is the cause of currents? They may originate from tidal effects. They may originate from wind forcing that may cause a movement of water. Currents may be also originated by temperature gradients, and in particular, the gradients, the day-night temperature gradient can originate currents. It can also come from gradients in salinity. And of course, in river estuaries, we have a current which is generated by the inflow, the river inflow. Usually, we should consider three types of forcings. Besides the pressure and drag, there are also the forcing caused by dynamic instability, the flutter effect, resonance. We forget about resonance here. Okay, the only thing that I would like to mention is that also currents can follow a period, can have periods. Usually the period of currents, it's a long period, a very long period, like night, day, or tide. If you have reasons to suspect that the period of currents may get close to the characteristic period of ships, then you have to also consider the dynamic effect. Unless you are in this very specific situation, which may come by these forcings that you see on the screen, water flow from river estuaries, which may be periodic, tidal effects, which are periodic. So, but if you are not in one of these situations in which the period of currents may be close to the characteristic period of the ships, if you are not in this situation, you can forget about the dynamic effect and you can only consider pressure and drag. Okay. And otherwise, you have to consider resonance. And we, as I said, we will discuss resonance further because there will be a lecture that will be dedicated to that because it's an interesting, indeed, it's an interesting matter, resonance. So if we are in the condition of taking a simplified approach, no dynamic instability, now we can simplify the current force by considering only two components, one horizontal force in the longitudinal direction of the ship, like we did for waves, another in the transversal direction. And we also have to consider a moment around the vertical axis, because here, given that, the current is a movement of mass, indeed, it may originate a rotation of the ship around the vertical axis. We are not expecting this type of rotation with the wave forcing. It is usually, it's negligible, but with currents, which is a consistent mass movement, we may also expect a rotation, okay? All of them are again applied at the ship's center of gravity. It's a simplified schematization because this allows us to get the usual two empirical relationships, three in this case because there is also rotation, which allow us to take the simplified route, okay? Okay, so these are the three relationships. They are very similar to those that we have seen before, okay? Again, taken from the Spanish standard, but this is only referred to pressure. These three relationships only give you the forcing given by pressure. I'm not including the forces included by drag because the relationships are more complicated, and I don't think it is really useful that we add empirical relationships over empirical relationships. So if you want more details on dragging, refer to the link, the Spanish standard. There is everything. The Spanish standard is quite a long document, so it is not easy to find out the page where you have to refer to, because also it's you cannot use text search in this document. But anyway, you will manage if you need it. It's unlikely in the short time, so this is also why I didn't want to include it here. For this relationship that you see here, the first two ones are the horizontal components, and they are derived by following the same concept that we saw earlier. There is the velocity of the current squared that gives to you an estimate of the energy of the current. So the forcing is proportional to the energy. And then there is the density of water. Once again, there is coefficient, which CTC that you see here, which is a shape factor for the calculation of transverse currents. Okay. And so a shape factor, velocity, the area of the ship exposed to the current along the transversal direction, or let's say it's along the transversal direction is the product ALC times sin phi. ALC is the submerged area of the ship exposed to the current projected over the longitudinal plane. And then if you take this area times sin phi, you have the component of the area along the transversal direction, which is quite relevant. I mean, the side area of the ship, which is exposed to the current, is a relevant area, okay? So this for the computation along the transversal direction. For the computation in the longitudinal direction, it's the same thing. Of course, the coefficient changes, the shape coefficient, and you don't have the angle here. Why? Because the area along the transversal direction, it's much lower than the area along the longitudinal direction exposed to currents, and therefore, in a conservative approach, we don't need to consider the cosine component here. We don't have to multiply by the cosine, because we can take the whole area and assume that the whole area is exposed to the action of currents. So this is why you don't see any angle here, because ATC is much lower, and therefore we can take the conservative approach and assume that all the transversal area is exposed. And then there is the rotation, the moment. Again, we consider only the component due for the rotational moment. We only consider the component due to FTC, the forcing in the transversal direction, because the other component is negligible. And basically, we take the component along the transversal direction and we multiply it by the eccentricity, which is L is the ship length, and the KEC is eccentricity, okay, which is varying from minus, it's an eccentricity coefficient. So it's varying from minus 0.17 to plus 0.17. This is a coefficient that is given by the constructor of the ship. It's a characteristic coefficient of the ship. Okay, basically, if you multiply the eccentricity coefficient KEC times the length of the ship, you obtain the eccentricity of the transversal component of the forcing. Here there are some further specification on the computation of the velocity of the current, and let's forget it, but let's remember the order of magnitude. So a typical velocity for a current, usually a strong current, has velocities that may vary from 1 meter per second to 2.5 meter per second. And these are quite strong currents, okay? But keep in mind that in some of the cases, you may get indeed strong currents. And also in canals, into harbors, where you have inflow of rivers, indeed, you may get some relevant currents. So once again, these formulas, you don't need to remember them. Just remember the concept, and remember that in this case, we also consider rotation. Finally, there is a final section, impact. We don't discuss this. Again, we don't discuss this. Actually, it is a forcing that may be significant, may be important. It's due to the fact that the ship, while berthing, even without any accident, they basically have, by definition, they impact the berth. And the computation of the forcing must be related to the kinetic energy with which the ship approaches the berth. Kinetic energy which depends on the mooring velocity, on the berthing velocity, sorry. And the berthing velocity, again, depends on the type of ship and depends also on the type of berth that you are designing. So depending on the berth, depending on the ship, you get an indication of the velocity with which the ship approaches the berth, and then the velocity means energy, and you estimate the forcing due to the impact by considering the energy of the ship. But the approach is quite complicated. There are empirical relationships, of course, but I didn't want to give them to you. I just want you to remember that the impact, the forcing originated by impact, is an important forcing, must be considered, and there are empirical relationships or numerical models, more complicated and for more complex assessments, which give to you an indication. And then I think we can say that we are done with this forcing estimation. And also we are done for the break. Do you have any question? Okay, let's take a 10 minutes break. Okay, so let's refer to our exercise now. Which, as you may remember, is the computation of wind actions on a moored ship and mooring forcing. So what we did so far is to get familiar with the RStudio, which is here. So we discussed how to use RStudio for making computations into R. And we didn't start actually making our exercise, developing our exercise. We just did some basic computations here. And I still have in the global environment these numbers, which I think I should remove now. So let me remove from the console A, data 1, data 2. Okay, I cleared the console, and now let me go back to our task. So the task is to first compute the wind forcing, and here there is the solution that is explained step by step in the web page. So first of all, we have to apply this relationship here by simply substituting to each of the independent variable the corresponding value. So you see here that we have everything. In our case, CW is 1.3, AW is 950 square meters, because these numbers, this data, this information was given by the text of the exercise. And also you see here the solution. So what we are expecting is to get wind force, which is given by the relationship, and it's about 510 kilonewton. Now let's apply into R the same relationship. This is very simple, okay? This is very, very simple. So let's open also the R code, which is available here in a new tab. And you see here the R code, which it is articulated through a function. And we learned what is a function, because last time we wrote a function into R that computed the sum of two numbers. So what is the essential structure of a function? We need to define a function name, and we need to give the arguments of the function. Remember that into R, any function has arguments, okay? We could make the computation without writing a function. What I want, the reason why I want to write a function is that you learn how to do it, okay? So, first of all, we need to give the input data that are fixed. The other input data may be given as arguments of the function, but first I need to give the input data that are fixed. And these fixed input data are the coordinates of the bollards and the chocks. In order to give these coordinates, I want to create into R two arrays. The first one is called CB. So CB is the array of the coordinates of the bollards. First, where can you find it? Here. These are the coordinates of the bollard and the chocks. So what I need to give into an array is this 6 couples of numbers. So minus 50, minus 10, minus 35, minus 10, minus 5, minus 10. If you look at the instruction in the R code, sorry, in the R code, it's here, you see that indeed you have these coordinates here. X coordinates in the first column, Y coordinates in the second column. The way we obtain this array is by binding columns C bind. And the two columns are the two vectors. This one, which I am selecting now of the X coordinates, this one for the Y coordinates. Okay, so what I'm doing, I am binding the columns given by two vectors, one column for the vector X, another column for the vector Y. So let me just copy this instruction, copy, and I can put it into the console. The console, not the script, because I mean, this is just an instruction to be given once. So here I am pasting, paste, doesn't take it, just 1 second, and let me understand why. Okay, now I pasted with Control V, and here I got the vector, the matrix. Let's look at the matrix. You see, here I have the two columns that are binded. And these are the coordinates of the 6 bollards. And now I need to define the coordinates of the 6 chocks. So let's take the second instruction. Here, chocks. Okay. Copy. Now, let's go here. Paste, Control V. And these are the coordinates of my chocks. This is simple definition of input data. Okay, good. We may want to save it now, just because I want to make sure, okay? So save all. I am using the menu, save all. Okay, everything is saved, okay? And you can see here in the global environment, you can see the two arrays, the two matrices that I defined. Perfect. Now we can go to the definition of the function. And in this case, I would go on the script. Good, so function here. I call the function moorings. It's a function, and then I give the argument. Let me copy it, and let me paste it now, okay? Okay, now, let's look at this instruction here, which I placed into the script. Again, not in the console, because this is something that I prefer to save. Now, what are the arguments of the function moorings? You see that the arguments are the length of the ship, and a default value is given, 92.6. Another argument is the side area, and the default value is given. And then there is the angle alpha, which is 90 degrees, is pi divided by 2. Pi into r is, look at the console, pi, it's pi. Okay, it's defined in this way. CW, waterline length, and the coordinates of the bollard. I gave a default, which is CB, coordinate of the chocks, cross area, and eccentricity and drop elasticity module and drop tension, because this function allows me to compute not only the wind forcing, but also the decomposition. Good. Now, given that the function is composed by several instructions, I prefer to open a curly bracket. Just 1 second, I need to find out how. Okay, I was working in the console. Just 1 second, it's here. Okay, the curly bracket, I obtained it through Alt-GR. Alt-GR is the key that is placed on the right of the space bar. And while I keep Alt-GR pressed, I pressed the number 7 in the upper part of the keyboard. And then I obtain the curly bracket. I think one can obtain the curly bracket also in this way. Let me see. No, this is square bracket. 1 second. Yeah, and there is another way to get the curly bracket, and it's to press Shift and to press square bracket. Anyway, you have to find on your keyboard how to get the curly bracket. Maybe that you have an American keyboard and the curly bracket is explicitly typed using a specific key, which is visible. In my keyboard, it's not visible, so I don't know where the curly bracket is if I just look at the keyboard. Okay, now let's write the content of the function. Let's refer back to the R code. Here you have 2 comments. We can copy them. And then up to here. Copy. Paste. Okay. Now, computation of wind force is easy. Okay, we have already everything here in the argument of the function. So let's go here, because of course now we have the code that is already written. And in case you don't have a code that is already written, you have to write the code by yourself, which would be better because you learn better. If you write the code without making a cut and paste like I'm doing, if you write it, your learning is improved, of course. We use the cut and paste here because we want to speed up the process. But actually, what we will do in a moment is to pass on the Python console. And for there, I don't have any written code. Okay. Good. Okay, let's copy this. Copy. And let's paste it. Okay. Now, let's forget for a moment the code, because the code is continuing in my website here. Sorry. The code here is continuing with the computation of the rotational moment, etc. And then with the computation of the mooring forces. Okay, I don't want to move forward now because I want to stop here for now. Okay, computation of wind force. So the function is concluded. I mean, here I can stop now. If I only want to get the wind force, it's already computed. It's there on the screen, and I can stop here. But if I want to stop here, I have to tell the functions to return back to me the value of the computed wind force. So let me write here, return PV, PY, sorry. I am returning the function, the value. And then I can save all. and then I can source the function. I write here, let me clear the console. I click here, source, and you see that it's computed. And now, if I want to run it, it's very easy. I can do moorings, and then I give no argument. Why no argument? Because I have default values for all of them. And you see the computation is done. Let me say one thing. We are here using a code that is already written. And I mean, I could, I did it step by step, but I could do it in 1 second. Let me cancel the function. Let me delete it, okay? Let me start from scratch. If I have the code already written here, I could let's suppose that I found this code on the web. That's fine. I can copy all of it up to here, copy, and then I can go here, paste, and that's it. The only thing that I need to add is return py and the curly bracket to close. Good. And then I can source it and then make moorings. So if you, sorry, I need to make mooring in the console, not here. Moorings. So if you find a code on the web, you just have to source it into R, and then you can use it. And indeed, given that R is supported by an open source community, you may have several opportunities to find codes over the web. And you can do that. This is one of the advantages of R. If you find already something written there, use it. Of course, check the reliability of what you're using. Check, try to understand what the code does and try to evaluate if you can trust it. But on the other hand, there are also, let's say, certified sources over the web from which you can take whatever you want. Now, let's suppose that we want to apply moorings with a different data. So I can say, for instance, moorings side area equal to 1,150. And you see that the result is different. And if you specify only one parameter with a value that is different from the default, then the other parameters, the other arguments are kept constant. Oh, now let me just show you. Let's suppose that we didn't give a default for side area. Okay, side area, I removed the default. You see, I removed the default, and then I source it, and then I just type moorings without any argument. You understand that if the function doesn't have a default for side area, it cannot work, because if I don't specify side area as an argument, it cannot work. Let's see what happens. You see, argument side area is missing with no default. If I make, if I give a value for side area, I get it. Okay. Let's give back the default here of side area. Now I can source it. And if I give the default, the computation is done. Okay, very good. So I think we completed the first step. Now, before moving forward, because now we have to develop the core of the exercise, the composition of this forcing along the mooring lines. depending on the elasticity module, depending on the position of the moving lines, the geometry, etc. But before I move forward, let's remember one thing. We also committed to study Python, okay? And let's try to do the same thing into Python here, okay? The same thing that, I mean, computation of wind force. It's a simple computation. Let's do it in Python. Okay. In order to make it in Python, what I have to do is to open a Python console. And given that it's already open somewhere here, let me close it, okay? No, this is not a Python console. No, it's not open. Okay, good, good. Let me open a Python console. The Python console, I told you how to install it in the PC some time ago. What you need to do is indeed to install it in your personal computer. And it is found in the public domain. So you see Windows, if I look for it, it proposes to me an app, Python 3.11. It's already installed. And if I open it, I find something that is very similar to the R console, but of course, I don't know what are the instructions to be given. And we made some simple assignments. And if you may remember, A equal 2, and then I can make computations, etc. But it may look like something that is identical to R. But actually, it's a bit different, and we need to understand the difference. It's not the same thing. Using Python, using MATLAB, using R, it's not the same thing, because Python is a programming language, while MATLAB and R are platforms for making computations which are already pre-prepared. So we can make coding into MATLAB and R in their own language. But the benefit is that they are already pre-prepared. Like, for instance, we can save things in MATLAB and R. We can save the workspace. Python, by default, is not conceived for saving things. Python is conceived for executing instructions, executing computations, and printing the results wherever, into a file, over the screen, but they are not conceived for saving. They are not conceived to create a workspace. There is a fundamental difference between a workspace like Excel, Word, MATLAB, R, with different levels of user friendliness, and a programming language. A programming language, a code, is something to be executed. And if you save something, you save the code, meaning that you write a code that defines a variable, like here, A equal 2, okay? I defined a variable. And once I quit Python, it's not saved. And it doesn't ask me, would you like to save? Because it's not conceived for that, because any saving is occupying memory, is making the computer busy. When you reopen it, it is automatically uploaded. The code must be such that when you reopen Python, you execute the code again. So if you define a variable like A equal 2, you have to redefine it, which is not a problem if you have a code, okay? This is the first difference. The second difference is that a code, like to some extent MATLAB and R, is composed by modules. MATLAB is composed by toolboxes. And you have to upload these toolboxes before using them. But there is one thing to say. Into R and into MATLAB, they preload some toolboxes, because they think that there are some common, very frequent operations like square root, like logarithm, that are very frequently used, and therefore they preload it. So into R, into MATLAB, you have already defined the functions to make the computation of the logarithm, for instance. Into a programming language, in general, nothing is preloaded, or if it is something preloaded, it is very simple, like the instruction to define a variable. But if I want to define a vector, if I want to read from an external file, I have to upload the toolboxes. So into Python, it's essential, the first instruction of the code must be the uploading of the modules. Okay, so here, if I want to make mathematical computations besides the 4 basic operations, multiplication, if I want to compute the square root, I have no function defined square root. I cannot write square root of 4. It's not defined. You see, square root is not defined. So what I have to do is to upload this module. So what kind of module I need to upload into Python? And keep in mind, it may look to you much more complicated than MATLAB and R, but the complication is introduced because they want to save resources. Basically, Python wants to upload and occupy only the memory that is strictly necessary. As a result, when you make computations, Python is much quicker than MATLAB and R, which in turn are much quicker than Excel. So Python is a further level of evolution. Okay. And once that you can use Python, you can say that you are really coding into MATLAB, into R. You are coding, but with an easier approach. Here, you are really coding. Okay, good. Now, the problem is that the modules have to be installed in Windows. So, for instance, if I want to compute the square root, I have to upload a module that is called, just a second, okay, it's called math. So first of all, and the instruction that I have to give is import math, is the math module, is the mathematical module that allows you to make the square root, gives a lot of function, logarithm, etc. And I have to give also the name that I want to use in my environment. Usually, what we do is to use the same name. But if I make this import, I think I get an error. Let's see. No, it's not. Okay. It's already installed into Windows. Okay. And when I did it in my Linux machine, I needed to install it. So how to install in Windows modules? This is important to know. Okay, let me just do one thing, sorry. In order to work to install in Windows Python modules, you have to open a terminal. So you search in Windows Apps, terminal, which is the Windows console. I'm sorry, I didn't open it. It is the Windows console terminal. Still 1 second. I don't understand. Ah, yeah, okay. It was open but not displayed. Sorry, one thing. I opened 3 of them, so I want to close the other ones. Okay, so this is the Windows terminal. You see Windows PowerShell, and it's the Windows console. It's a way to interact with Windows more directly and to make additional installations, because otherwise I couldn't find. Let me see if I can make the installation of the modules directly from here, NAMPI. Yeah, okay. Maybe that I don't need the terminal then. Okay, let's forget about the terminal. And the modules can be installed directly from the Windows menu. So if I search, for instance, for NAMPI, NAMPI is I don't have to make a search. I have to get it here. NAMPI. Okay, you see that there is here Scarica, and then we can install it. What is NAMPI? NAMPI is a package that allows me to manage data into Python. It gives to me functions to upload data from files, to create arrays, etc. So I can download it, and I get the installer somewhere, installing NAMPI. And let me see if there is the download here. Actually, you see, what it tells me is to use this command from the terminal. So it is indeed needed the terminal. Okay, good. So let me open the terminal then. Terminal. The terminal is here. Here. I can do pip install NAMPI. This is from the Windows terminal. And this is the instruction that it was given to me here, installing NAMPI. Okay. And you see, it tells me that it's already installed because I installed it during the break. Okay, once that you installed it, you can close the terminal, and then you go to Python, and then you make import NAMPI has NP. Good. So I imported the two modules that I need. Now, if I make sqrt4, okay, it is not sqrt, but it's math.sqrt. Okay, and this is the result. But I could get this result, I could get this function because I imported math. Now, math, I don't remember how to get pi. Let's see. Math pi. I think, let me do like this. Okay, this is the way to get pi, for instance. But again, I needed the module math. Okay.
Then we have several things, right?
Several things, yeah.
Not just.
No, several. And in order to get the list, you have to, as usual, to go on a Google page, like here. And then you search for math module Python. And then, okay, this is a course. Let me see, mathematical function. Here it is. And here there must be the list of all the functions. You see? And I think there is also math log. Let's see. I'm just guessing, okay? Oops, sorry. I don't remember how to clear the screen. Anyway, it's no problem. Math log 10. I'm just trying. You see, I got the logarithm, but if you look there, you find everything. I'm just checking how to clear the screen. Let's see, clear. No, okay. I want to clear the screen, so let me just clear screen Python. Control L, but I tried with Control L and I couldn't get anything. Okay, let's see. Clearing the screen, OS system, GLS. Let's see, OS system, GLS. No. Okay, I have to make import OS. Let me see. Import OS. No. Let me try this. Yeah, now it's okay. Okay. But in my PC, it works Control L. It may be a problem here with the keyboard. I don't. Okay, so now we have imported the two modules that allow me to make some computation. Now let me just try to repeat our exercise here. Okay, so let me define the variables. The variables are WM equal 92.6. WM equal 92.6. And side area 950. Side area is equal to 950. And then alpha is equal mass dot pi divided by 2. And here, I mean, I can do this. Okay, CW 1.3. And LWL is equal 117. Ford Bollard is equal CB. The only thing is that CB is not defined. So let's forget about this for now, because I don't need this for computing the wind forcing. Cross area equal 90. And I think for now I can stop here. And then I can compute CW by using this formula here. Okay, and so let's make it Py is equal to CW, which is defined, CW times side area times, okay, the sin, I think it is math dot sin alpha. We have to try. I'm not sure the function is correct. I think so, but square times gamma W, it's 0.01225. Okay, and yeah, times, okay, VW, okay, divided by 3.6. This is to convert units, square, divided by, parentheses, 2 times 981. I think it should work. Let's see. No. 1 second. Parentheses are correct. Okay. I think elevation to the power, it should be like this. No. Let me check the power Let me check the power. Okay, should be the second one. This should work, but it still gives a mistake in. Let me put so you can see unsupported operand types for power. Okay, let me try this. 2.0 maybe. No. PW, just 1 second. Side area. Must see maybe. Let's see. Let's see. No, this is correct.
Maybe you can use extra parentheses.
Sorry?
Extra parentheses.
Okay, let's see. 1 second, I wanna clear the screen. Extra parentheses, you said? Sorry. Okay, this should work in this way. Let's see. Okay. Let's do this. No. And if I this here, no. Let me check. I think it must be a stupid mistake, and I'm quite sure. Let's see this. Let's try. In order to detect where the errors are, it's better to split the computation in chunks that are smaller, and then you identify where is the mistake. Okay, it's still good. Let's still good. So I think the problem is here. It must be here. Yes, it must be here. So
But
you mean here? One second. I don't think it's here. Just 1 second that I wanna clear the screen. So 1 second. I want to get again the formula. Okay, so this one is still mistaken. Let me see. I think the problem may be the parenthesis here. Let me just check. No. Sorry. I forgot, you know, yeah. When programming, it's really a matter of stupid things. The reason why I try to work while lecturing with the pre-prepared codes is just to avoid to lose time in identifying trivial mistakes. On the other hand, there is to say that if you resolve trivial mistakes, you learn a lot. So, I mean, there are two sides of the medal. Now, PY, you see the computation is correct. So we were successful. And I think in Python, we can close here for now. Okay. And so the message that I want to convey to you, first of all, as I already mentioned, the larger the number of tools that you learn to use, and the more robust is your CV. So it is not time lost to learn one more platform. It is indeed something that you may think now doesn't deserve dedication of time, but I tell you, this is really coding. It means that you have to upload everything you need, and you upload only the things that you need, and what you produce at the end of the story is a code that it's very efficient. And once that you get used to it, it doesn't really take a long amount of time. There are some modules that are frequently used, like math. Math, you can put it as a default in your coding, in your, I mean, in any code, automatically you put input math as math, and input NumPy as NP, and then you are already there. And for plotting, same thing. You have to input, and we don't discuss it now, we have to upload a module that allows you to make plots. So it is something that it requires a lot of time at the beginning, but at the end of the story, with a reasonable employment of time, a reasonable dedication, you get one more standing item in your, outstanding item in your CV. I mean, if you can write expert Python programmer, it's and you don't, it's a plus, and you don't need a lot of efforts to get to the level of expert. We are already quite close to there. And I tell you, I am learning with you because I tried in the morning to make mathematical computations, and I went over the web, and it's very easy to find help. So basically, what I told you before, here if we close Python, we lose everything. So actually, it would have been better to copy these instructions over a text file, over a script, which can be executed very quickly. Like in R, you make source. Here, you can make something very similar. In my case, I didn't copy anything, so I wonder whether it's possible to get an history. Let me see. I don't think so. I don't think it is so easy. So let me check. Because what I really would like to do now is let's try to save it, everything, okay? So let's write save Python commands. How to save a Python interactive session. I think this one, ePython. I don't want to use ePython, which is something that it's save. Okay, but this is ePython is a module that I don't want to. Okay. Import red line. Okay, let's see whether import red line. No, it's a module that needs to be installed. So it's not an there is not an easy answer to this. So now let's forget about it. Okay, I go out, quit. I don't remember if it's quit or exit. Let's see. I go out and everything is lost. For next time, we will discuss how to save everything. The easiest thing to do is any instruction that is useful is copied into a script, like we do for R, that we write on the script window, the instruction that we want to save, the instructions that we want to repeat the next time. Okay. Okay, now we have like 10 minutes, a little bit less than that. And in these 10 minutes, I want to anticipate what we need to do as a next step, which we will do first in R to solve the exercise, I mean, and then in Python. Okay. Let's see. Exercise here. And I go to the web page. Where is Just 1 second. Here it is. Now here it's explained everything. And you see, after the computation of the wind force that we already did, there is the computation of the rotational moment. And in order to do that, we need to get an indication of the eccentricity, which can be estimated from this abacus here. Okay. So depending on the angle of approach, there is an eccentricity coefficient. And then there is, we multiply the eccentricity for PW. I think here there is something that I need to correct. This is PY, okay, the force that we computed here. And then the length of the water line. So basically, I take the wind force and I multiply the wind force for an eccentricity coefficient that is estimated from the abacus, and then I multiply by the length of the water line, which is given. I have it in the data. And then I get the rotational moment. And then let me just make a correction of this one. I hope it's still there. It's still there. Yeah, it's still there. Just 1 second. I want to make the correction of this because I didn't notice that. And if you see any other need for corrections, just let me know. I much appreciate it. Because, you know, it looks like it's easy, but actually, when you write from scratch new pages, it's not so easy, actually. Okay, log in. And then let me edit it. Rotational. Okay. Okay, this is corrected. Now, computation of mooring forces. Let's have a look at this. The theory is described here below, okay? And the application, there is the R code, which is the same code that we were looking at before. Okay, computation, it's a complex problem because the ship is a rigid body with 3 degrees of freedom, and which is berthed with elastic mooring lines. We refer 3 degrees of freedom because we don't consider all the 6 degrees. We consider only 3 degrees of freedom here. And we refer to the computational method that is proposed here. And there is a document explaining it. And we consider an even simplified case where the ship has 2 degrees of freedom only. And then we assume that the elastic modulus of the mooring lines does not vary with mooring forces. Okay, it's constant. Mooring line arrangement is symmetrical with respect to the y-axis, like in the scheme here. You see, it's symmetrical with respect to the y-axis. Okay. The y-axis is the transversal axis. Yaw moment MW and lateral force PY are applied at the ship's pivot point. The mooring lines are assumed to run horizontally. If you want to relax this assumption, there is here a link. Now, the step-by-step procedure is derived from structural mechanics. It's the composition of a forcing along elastic directions, elastic mooring lines. And it's quite complicated, and it's described in the two links that I provide above. As I told you, we are not interested in understanding the theory behind it. The theory is structural mechanics. We are just interested because we need to apply the relationship in what we have to do step by step. So please, by next week, have a look at these steps. Some of them, you don't need to learn anything by memory. Some of them are impossible to understand the concept. I mean, if you don't look at the references and if you don't get into the structural mechanics problem. But what I would like to do is that just have a look at the relationships. And then next time we can assume that we accept that we have to apply these relationships here, and the only problem that we have is translating into an R code. Okay. And I think we can stop here. So today I made quite 15 minutes less than scheduled, and I will recover it. Okay. The nice thing is that now the train timetable is back to the default. So next time I can make half an hour break. Okay, any question? By the way, this is the fifth lecture, so I think next time I will give to you the questionnaire, the survey of students' opinion. So, and I will give you the instructions when I will give it to you. Okay, next time is next week. We meet next week, is the last day before the Easter break, and then we meet again the first day after the Easter break. And the timetable, the calendar is like in the website. Okay, thank you very much.